Hi, my name is Mimi, and today my project is about Y quality prediction using machine learning algorithms. We all know that Y is an alcoholic drink that is made up of fermented grapes. The two popular types of Y are red Y and white Y. According to experts, the Y is differentiated according to its smells, flavor, color, but we are not Y expert to say that the Y is good or bad, right? So what will we do then? Here the use of machine learning comes into play. But before we dive into that, I'd like to walk you through a little bit about the data set. So after I downloaded the data sets from the UCI site, University of California, Irvine, there are two data sets here, the red Y and the white Y. They all have the same variables. So each data set has 13 variables that can be grouped into categories of Y characteristic. So for acid category, we have fixed acidity, volatile acidity, citric acid. The sugar category will be residual sugar. Chloride is the salt category. We have chemistry categories, free sulfurs, dioxide, total sulfur dioxide, pH, sulfate. And for the physical characteristic, we have density, alcohol. For the rating, we have quality. What I would like to do is I would like to merge the two data set into one data set. So this part right here is all about merging data set. Before we do that, first thing I create an extra column for each data set. I call it good quality that assign one for the quality Y, which have quality score of 7 or above and 0 otherwise. And then we create a columns that a vector column of a Y name so that we know which data set all the rows from. And last, we combine the two data sets together. This last part right here, I remove the quality column, this column right here, because we're gonna have a good quality column right next to it. And then the last column is the color column for red or Y, right? Because we already have a good quality column, we don't need this column. We can remove it from the data set in case we accidentally include it as a predictor when we perform classification. The second part is data exploration. So we have one giant data set, red Y stacked on top of a white Y. Okay. Now I would like to count the quality of the Y. So there are 1,277 good Y that we label as 1, right? And the rest will be not so good Y we label as 0, right? So of 6,497 observation, that's roughly 20% is identified as a good Y. Here is the descriptive summary of all the continuous variable. I also create a histogram of quantitative continuous variable. From observation, we can see that all variables have a uniform, unimodal distribution. Some are bell-shaped, such as pH variables here. Total sulfur dioxide, not perfect normal, but somewhat normal, or citric acid. Okay. The other are more lightly right skewed. Next, we plot a correlation matrix between quantitative variable. So here is the heated map for correlation matrix. As we can see, there are only 3 pair of variables have correlation above the absolute value of 50%. Namely, the correlation between residual sugar and density, free sulfur dioxide and total sulfur dioxide, and lastly, density versus alcohol. Right. Since we don't see a lot of multilinearity, which indicate no redundancy in the information in the data, therefore a dimension reduction technique such as principal component analysis is not needed. The next step, we're gonna dive into classifications. As I mentioned in this project, there are 5 classification techniques I like to go through. They are logistics model, simple decision tree, random forest, linear discriminant analysis, quadratic discriminant analysis. But before we start up our classification techniques, we will create a 70-30 split of the data set into training and testing data. Right? And training data was used to fit each model for the particular classification technique. Each fitted model was then used to predict a good quality Y classification on the testing data. We are using the confusion matrix to evaluate the performance of the classification models. So here, the first model, logistics regression models. We start by creating logistics regression model to predict good quality and compare it against with the rest. So here is a confusion matrix. This right here is the table of counts. 3,478 observation instances was correctly predicted as class 0. So this is a true negative values. For true positive is 247, meaning 247 instances was correctly predicted as class 1. Okay? And this value right here is a false positive. 647 instances was incorrectly predicted as class 1 when they was actually class 0, right? And this right here, 176 instances was incorrectly predicted as class 0 when they were actually class 1. Okay. For the statistics, we have accuracy, 81.9% of instances, both true positive and true negative, out of the total number of instances. And we have the sensitivity of 27.6%, meaning is correctly identify 27.6% of the actual positive. And the last specificity of 95.1%, meaning is correctly identifies 95.18% of the actual negative. From these statistics, we can see that the model is much better at identifying negative instances than positive ones. So let's take a look at the predicts on the test data. Here is the accuracy, is pretty similar to the train one. Here the sensitivity, same thing. The specificity, same. Right. So the accuracy on the test is very close to the train set. The difference is very little. So this suggests the result on the test data are consistent with the model performance in the training data. Right. However, the sensitivity is quite low, right? 27%, that's quite low, suggesting there's a large percentage of high quality Y is missing. The next model is a decision tree model. We create a simple decision tree model, predict good quality. Again, we're using all the variables. Right? So here is a confusion matrix on the trained data set. Accuracy 84%, sensitivity 33.5, specificity 96.4. So it's slightly better. The number is slightly better than the last model. Let's take a look at the predict on test set. Similar numbers for these three components. The third model is a random forest. When we fit the models for the random forest and we call it, there's a little confusion matrix in the model here, but these are just count. We want to pull up the statistic as well. So let's take a look at the confusion matrix on train. Here the accuracy is 88%. So far is higher than the last two. Same thing with sensitivity and specificity, right, is much higher. Is higher than the last two models. Let's take a look at the predict on the test set. Similar result, 87 for accuracy, 54, 95 right here. Okay. The next one is linear discriminant analysis. LDA is a dimensional reduction and classification technique. Right? It is used for classification tasks where the goal is to predict the class label based on their characteristics. The main objective of LDA is to find the linear combination of features that characterizes or separates two or more classes in the data set. Okay. In order to perform the LDA model, there are several assumptions about the data, including the classes are normally distributed. Right? In our case, we have two classes, class 0 and class 1. So classes are normally distributed. The classes have the same covariant matrix. So the LDA function through the mass package was used to fit the LDA model here. And take a look at the confusion matrix for the LDA model. Accuracy 82%, sensitivity 93, or roughly 94, specificity roughly 33%. Right. For the predict on test data, similar result here, similar result. Okay. The last model is quadratic discriminant analysis, QDA. It is similar to LDA in a lot of sense, which is to find the decision boundary that separate different classes in the data set. However, it is more flexible in terms of the assumption. In contrast to LDA, QDA relaxes this assumption and allows the different covariance matrices for each class. Okay, so here we take a look at the accuracy, sensitivity, specificity. The accuracy so far is the lowest of all five. Right? So what is the best model? It's hard to tell. It's hard to pinpoint the best model here of all five, because we have to take into account of the specific requirement of the individual problem, right? Sometimes we have to consider the trade-off between different metrics and choose the model that best align with our goals. So here we take a look at the summary of performance of all five models of the metrics accuracy, sensitivity, and specificity. Recall accuracy is the proportion of correctly classified instances, right? Sensitivity is a true positive rate, and specificity is a true negative rate. We take a look at the table. Random forest has the highest accuracy, 87.89%, indicating that it's correctly classified the instances most often. However, accuracy alone is not account for the best model, right? LDA has the highest sensitivity, indicating that it's correctly identify the high proportion of positive instances. If your goal is to identify positive instances, then this is a good model. Okay. Random forests have high specificity of 96.1%, indicate that is correctly identify a high proportion of negative. If your model is to identify the negative indices, then this is a good model. Decision tree also show the competitive performance across all metrics. Ultimately, the choice of the best model depends on the specific goal for individual interests. But based on this table, I would say random forest is the best fit model so far, at least for my interest. Um, so those are my classification technique analysis. Okay. For conclusion and future work, so for the analysis of water quality on the 6,497 observation, our interest is only in distinguish between high and low quality of Y, right? Out of all 11 variables. For future work, we can consider a different technique such as Bayesian classification or neutral network. Thank you for listening.